Great. So welcome to this fifth lecture on NLP with deep learning, and today we're going to be talking about. So far we're just touching the basis of deep learning, how to train these networks, and basically everything like general, except for the task in the first lecture. And today we're going to touch like very specific specific networks, or basically specific problems in deep learning in natural language processing, which is the intersection, like why deep learning is actually, why deep learning become very popular and very powerful for doing things with language. And today we're going to be talking about language models, which is basically nowadays the paradigm of doing things with language. And we're going to be talking about word embeddings, which is a very nice representation. So let's start with the first one, which is language modeling. And let me see. Oh, there is no pointer here. Why is that so? No, there is a pointer. Okay, so we'll start with something which I call classical language models, or might be like old school or count-based language models. But I mean, raise your hand if you had this language models intro in Intro to AI last year or 2 years ago with language modeling. So there's this course Intro to AI. Did you take it? Yes. So one person, only two persons. 3. So I gave a lecture, like a single lecture on language models, which was these count-based language models. Do you recall that or not at all? A little bit. Okay, good. So we're gonna refresh this a little bit, just a little bit, because that's not the goal. But we should be talking about language modeling like in general ways. So the goal of language modeling, as it has been conceived many years ago, like maybe in the 80s, is to look at language as some, let's say, probabilistic model of language, so to say. So let's model language as something which can be, assign probabilities to, and we can reason about how probable is something versus how probable is something else in language. And the language model, its main task is basically to assign a probability, so some value of probability to sentences in a language. This is a very generic definition of a language model. And for example, like we might be asking the language model to tell me, okay, what is the probability of seeing the sentence, the lazy dog bark loudly? So what do you think is the probability of the sentence in a language? I mean, it's hard to tell. Yeah? 20%. So you would say like everything, all the sentences you see in English, 20% of them would be the lazy dog bark loudly. You are using this very often. Okay, so in your language model, every fifth sentence would be the lazy dog bark loudly. Yeah, interesting. I mean, I would like to see your WhatsApp chats. Like, every fifth sentence is the lazy dog bark loudly. So the probability might be something. I mean, probabilities are hard to tell because this is a model of the world. This is not the reality, but we somehow estimate them. We'll get to that. So this is the question we're asking. Okay, this is really weird. Or any other way, it's like assign a probability for the likelihood of given word to follow a sequence of words. So this is basically this paradigm of like, what is the probability of next word being something after I've seen a couple of words? So for example, what is the probability of seeing the word barked after seeing the sequence the lazy dog? Now the probability must be much harder because this is a conditional probability. So everybody knows what is the conditional probability? Joint probability over the marginals. Good. There is an appendix in this, I guess, in these slides, just for a refresher. Like if you forgot some of these concepts, just scroll down and you will see it in the appendix. Okay, so here's an example, another example. Start with the sentence. So I was at the party at Joe's place last night, but man, I was so tired. So like at about midnight, I said, Joe, I am blank. And now the language model should tell you like what is the probability of the k plus first word being equal to something from the vocabulary, given that we observed the first word being so, the second word being I, the third word being was, and so on. Okay, doesn't make sense? Like your condition on the probability of seeing something before, what is the probability of seeing the next word? Or the probability of assigning the probability to each of the word of the vocabulary. So basically we have a vocabulary of some size, let's say, I don't know, 50K. And for each word of this vocabulary, we're asking, what is the probability of picking this word after seeing all these previous ones? And of course, I mean, naively, we would say like the higher probability would be for these words, like, oh, I'm leaving, I'm out, I'm calling it a night, I'm gonna need home. And of course, some lower probabilities will be for words that don't make sense in this context, even like semantically. So I'm hungry. I mean, yeah, that's not what you're telling a friend if you want to leave. I'm hungry, but maybe you can. Who knows? Maybe this is likely, but maybe not. Joe, I'm in love. This is also very strange, but why not? But something which is like even syntactically wrong would have lower probability. Like Joe, I would be somehow low probability because it syntactically doesn't make sense. So this is the language model paradigm, sort of. Any questions? Intuitively, it should make sense. What is the probability of seeing next word after seeing some previous ones? Okay. So formally, we have a sequence of words, which we're using this colon for sequences. So 1 to n, which are some words, and we are asking for this is the joint probability. So what is the probability of the entire sequence of words? This would be like the example of what is the probability of seeing a sentence, the lazy dog barked loudly. So in your example, you would say, okay, this probability of the joint probability would be 0.20 something. But usually the probabilities are very low because you have so many. I mean, just think about it conceptually. You have the vocabulary of 50,000 words, and if you have a sequence of n words, even like uniform probability would be something 1 over size of the vocabulary times length of the sequence. Not like powered, basically, like to the power of the sequence length. So we have very low probabilities, but what matters is like which is more likely than some other. And of course, we misuse the notation, and usually, if you this is like if you're depending on on probability theory, like depending from which angle you're coming to that, you can use very different notations, very different terminology. You can call it probability over some random variables. You can tell it random variables which have some distribution function. You can tell it like measure theory stuff, whatever. So everybody's misusing the terminology. So pick your own kind of model of understanding probability and just follow it and try to map everything what we see here to what you understand already. Okay, so this is the joint probability, and of course we can, if you have joint probability like I don't know, P of A, B, you can factor it into conditional probability like P A given B times P B. From the definition of conditional probability, you can do that, right? Or you can also factor it like P probability of B given A times PA. I mean, both is fine. It's just following the definition of conditional probability. So we have, again, here, this is basically joint probability of all words. And we can condition it, we can factor it into, like, the factoring means we have these different factors. So these are factors. Then we multiply them together. But some factorizations are usually better than some others. And one factorization is very useful. It's the left to right factorization. So which means I'm conditioning. So here we have here the sequence of words, and I'm conditioning the word based on the previous word. So the first factor would be the first word conditioned on seeing this. What do you know what that is? This S thing? Yeah. It's like a start symbol. So we introduce like very special symbols saying like start of the sequence or start of the sentence or something like that. So we're saying what is the probability of word 1 being something given the start of the sequence is the first factor times probability of seeing the second word after seeing start of sequence and first word, probability of the third after seeing start of the sequence and so on. So this is very nice factorization, basically left to right. But there's the equality, like everything is, we can do this factorization. This is just basically using the definition of conditional probabilities to have this sequence of probabilities. And eventually, we end up here with something which is almost as ugly as, what we started with. So we have very many sort of, let's call them random variables. We have a list of very many random variables, like n of them. And here we have n minus 1. And estimating this probability will be harder. So, because, the question is now, we have a very large space of, so we have a, let's say, if the sequence length is 50, we would like 50 random variables, and we would need to estimate or get somewhere the probability of this huge, long joint probability distribution. And it might be actually very hard to do it by learning from data. So we're gonna do one thing. We're gonna simplify this thing, this factorization, and we're gonna make some, let's say simplifications. So have you heard of a Markov property before? What is a Markov property? So there's a difference between I've heard about this and I know exactly what it is, right? Okay, I get it. So what do you think? So we are saying the probability doesn't depend on the past. So, okay, let's be more precise. So the conditional probability, so there's some conditional probability going from one state to another, but it doesn't depend on the past. What do you mean by the past? Like, it only depends on the current state, not what happened before. You're almost right, I would say, but it depends. So what you're doing is, if you have a, let's say, transition from one state to another, if you end up here in this state, you would be depending on all the previous states. So this is basically what we have here. You're conditioning on all the previous states. And if you take the Markov assumption, you basically say, well, you know what? I'm keeping this one, only the previous state, but I'm canceling all these previous kind of dependencies, because I'm considering that everything I need to go to this state is already present sort of in this state. So you're just basically, you're conditioning on only the previous state, which makes it very, so intuitively, does it make sense, Markov property? If you have some transition in some space, whatever that is. But for our language models, it's actually very, very nice. So you can think about this as being in a state and going to the next state, which is some word. So here's the problem again. I mean, we did some factorization, but still we have this very ugly long thing. So what we're gonna do is, we're gonna say that the next word depends only on some few last k words. So some k words previously. So we turn this thing, the very long sequence from the first word to the current word. So for example, having the whole sequence, how was your sentence? Oh, come on. The lazy dog. Okay, the lazy dog. Nice. Bark loudly. I mean, if you're saying this like, 100 times a day, okay. So what we're saying, if we want to predict basically this word, you want to assign probability of the word coming after barked, we're notating the whole sequence of the words, but we're just saying, well, k last words. So for example, one last word or two last words would be taken into account to predict the next word or to get the probability of the next word. Okay, does it make sense? Very cool. So that's where we get this approximation, and of course, everything becomes very, very much like shorter, easier. But now, think about this. Like, if you have just the last word and you want to predict the next word, I mean, aren't you losing something important here? So what could be the problem of doing this Markov assumption? We have the advantage. I mean, it will be, smaller factors, maybe easy to kind of estimate, but what is the disadvantage? You're losing the context. So is it a big deal, losing the context? It depends, exactly. So what do you think? Like, is it a big deal, or is it okay? I mean, there's a reason why it works. So what do you think? Where this could be a problem? Like losing in context. Yeah. Excuse me? Yeah, the next word could be not, of course, but it doesn't really care about the context that much. Maybe it does. I'll give you another example, like the very long dependency. So for example, you know, like say Alice went home, blah, 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 20 words. And then, and you have to choose whether it's he or she. And of course, if you see just a few words before, then both is possible, because the information for deciding whether it's she or he is very far away in the context. So it's called long-range dependency. Long-range dependency. So you're losing this information, obviously. So this is the context maybe you were referring to, like you're losing information from the context. But on the other hand, many situations in language basically are sort of local. Like you really care about just the previous couple of words. So you know we have this sort of locality property in language. So many situations, many phenomena are just basically local. So you can decide on just a few previous words to make some good decision about the next word. You don't really need a full context. But of course, the longer the context, the better. So I'm with you. So we're having this sort of trade-off. Like how big to look into the past, and what's the problem actually with this, like taking the whole context? So how do we estimate these probabilities in the first place? How do we get these probabilities? How do we know that, for example, I don't know, like the next word after the lazy dog and then barked, so barked given the lazy dog equals something 0.0022. Where do we get these probabilities? How do we learn them? Any idea? How can we learn these probabilities? Yes. You just look at your training data. So we have some training data. Everybody agrees we have some training data. What could be the training data? The internet? Okay, so do you need some special labeling of the data? Do you need somebody? Okay, so what do you need only? Oh, exactly. So you just take the words. You just take basically plain text. So it's very important. Like you don't need any labeling of somebody saying, oh, there's a dog, there's a cat, this is noun, this is whatever. You just take words. And you say like you're just gonna count them, counting occurrences. Oh, or you would say like you're gonna count like how many times we have the lazy dog barked, and what comes after. Okay, so you need some counts, the lazy dog, I get it, and then you need some counts of something else. Like counts which comes after, yes? Okay, you're saying this, and then so it's fraction of counts of your favorite sentence, your lazy dog. That's it? Oh yeah, this is so basically now we're basically counting the occurrences of this sentence and saying like, of course, how many times the words bark comes after this sentence is basically the counts, how many times I see it in the corpus divided by how many times I see the context. So intuitively, does it make sense? Like counting and dividing. Yeah, so intuitively it makes very much sense, and we take it from the internet, and of course we're changing all the words, so basically depending on the size of the context, we're getting so many parameters. So this is great because we just figure out how to do thing called maximum likelihood estimation. So this is exactly what we're doing, aka counting and dividing. So we take so these are the context words, and the words we are trying to get a conditional probability about. And we just count these occurrences, and we just count divided by the occurrences of the others. Okay. Any questions? Counting and dividing? Makes sense? So what could be the problem here? Yeah. So we didn't talk about this, I guess, yet, but you are right. So the data is very sparse. So some combinations some combinations of words will never occur. I mean, we talked at the beginning of all the lectures, like lecture 1, what makes language modeling, language processing hard? Yes, some combinations of words will never occur. So if you need to estimate this over all vocabulary, so how many times you will see in your corpus this I, depending on I, am. How many times do you think you will see this on the internet? I would say probably 0 times, because it's very weird. So the counts of this, or the probability of this, is 0. And you will get 0 probabilities for most of your random sequences of words, because language is not random. Like, there is some pattern, so you will see the probability of, like, I am tired. You will get counts for this sentence, obviously, but something like this, something which makes no sense, will be 0. So, and that might be a problem for using this language model to give you probability of some sequence, because imagine now you want to get, we have this, we want to see what is this probability of sequence something something, and you're multiplying these conditional probabilities, and now some of those will be 0. So you end up with 0 probability, but maybe there is some tiny little probability of everything. I mean, you would basically say, well, this sequence is impossible. Like, 0 probability is like, it will never happen. But it's kind of not true. I mean, it can happen. Like, who is telling what's right or what's wrong in language? Like, it could happen, but with some very, very, very low probability. So you need to think about this, like how to do that. And there's one little trick. How to add some probability which is non-zero is to basically add 1. So if you add 1 to this denominator, there is something very small. Oh, sorry, add 1 here. Sorry, add 1 here, and add the size of the vocabulary down here. Yeah. So what does it mean? The size of the vocabulary would be 50,000, for example. So if this never happens, the probability will still be 1 over 50k, which is very small, like it almost uniformly small, but it's not 0. So you will not end up with 0 probabilities. Okay, so it's called, I think it's called smoothing. Smoothing. It's not important. It's just that like these 0 probabilities are a problem. So we don't like 0 probabilities. Like everything should be somehow possible, but things which are more likely should have higher probability. But nothing should be 0. It's kind of bad. Okay, so any questions to training these things? Like, you get the internet, you do counting, dividing, and get your thing. Yes. Oh, this is interesting. How big is the K in language modeling? So we call this, wait a second, I need some room here. So we call this so-called n-gram language models. So this is the classical or n-gram language model. And n-gram, I think we talk about this, is a n consecutive tokens. So for example, we have bigram language model, which is the second word condition on the first word. So like a first order property sort of Markov property. You take just the previous word and condition only on the previous word. So this bigram language model. Then we have trigram language model, which is obviously third word given first and second, and so on. So this is the length of the context. Typically, like the classical n-gram language model would be until 4 or 5 max. Because for everything beyond 6 or 7, you will get something like 0 counts for most of these sequences. And it's becoming very big because you need to estimate this, the probability for every word in your vocabulary, like every combination of words. Yes. So here in this, if we take n-gram language, so your question is, whether language models in general, if you get text out of it, whether they condition it on the full sentence or just a few before. This is your question, sort of. So n-gram language models, exactly, they only condition on what they see in like the previous k tokens. If we talk about ChatGPT and other neural language models, they don't have this. I mean, they can condition not the full thing, but they do it in a different way. But I just wanted to start with something which is very simple, counting and dividing, and it has some. It actually will be. It can be very, very powerful language model in a way for modeling a language, but it's not as good as ChatGPT for different reasons. So this is it. Any other question to standard n-gram language models? It's very easy. You can implement it in like one script in Python. I think we did it in the exercise, in the last year. You basically take the internet, start counting and dividing, and you can use this for. Well, you can use this not only for getting probabilities of sequences, but you can use it for generating language. So I think we were generating, what was it? The IKEA. We were generating names and IKEA furniture, I guess, in the exercise. It was kind of fun. So you can look it up. I think I put it on GitHub. So, but the question is like, now we train these language models or this n-gram language model. How do we know they're any good? How can you evaluate them? Any idea? Let's say I give you, so there's some training data. Obviously, we need some training data. We would also probably need some test data, I guess, right? Typically, you evaluate something on test data. And then I give you a language model A and language model B. And I'm going to ask you, tell me which one is better. What do you think intuitively, which one will be better if I give you the trained model and the test data? What do you think? So the language model gives you a probability of the sentence. So which model should be better on the test data? So a model which gives a lower probability to sentences or which gives high probability of sentences in the test data? I mean, it should give, if it says, if for every sentence in your test data the model says 0 probability, it means it didn't understand the language, because the test data should be similar to your training data. So the model should tell you, well, this is probable and this is not probable. And if it says like everything is low probability, maybe it doesn't understand the language. I mean, it's assigning like low probabilities to all these sentences. So you want a model which kind of knows the language. So for all sentences, it will tell you, yeah, this has a high probability in a language. Does it make sense intuitively? So, okay, now we need to figure out like how to make a metric out of this so we can compare language models between each other. So there is one, and there's one metric which shouldn't be now surprising to you that much because we're talking about this already a little bit. So the trained model tells us probability of sentence S. So let's have n sentences in the test corpus, and each of them has a uniform probability of appearing. So each of the sentences appears in the test corpus with probability 1 over n. You have like n different sentences. So what is the probability of a sentence, a lazy dog bark silently? 1 over n, because there is no other such a sentence in the test data. Okay, so then we're gonna compute the cross entropy of our model. So our model is basically, this is our model. Our model is telling, oh, what is the probability of this sentence? So how do we compute the probability? I mean, we ask the language model, give me the probability of the sentence. We can do this. So this is basically, for the n-gram language models, would be a lookup in a table, for example, or maybe something else. But this is the model. The model is giving us, this is the API of the model, sort of. The model is giving us the probability of a sentence in a language. Okay, so I'm gonna compute the cross entropy of our model, which might look similar to something like categorical cross entropy, because we had there the logarithm, two probability distributions. I mean, it's basically the same thing, but expressed differently. So I'm gonna take the reciprocal of this probability, put it through logarithm, and multiply by the other probability, and do the summation. So a little bit of math, so I'm push this to the front. Then I'm gonna get rid of 1 over probability because it's ugly, so it's gonna be 1 over probability is a minus logarithm, right? So it's gonna be minus logarithm. Okay, I get this. And yeah, interesting. So I have this whole thing, and I'm gonna call this cross entropy. If you recall cross entropy for cross entropy loss, it's basically the same formula. It's like minus then the summation of one probability times log of the other probability, sum together. So this is a cross entropy, and for evaluating language models in general, we use something called perplexity. So this is 2 to the power of cross entropy. So we're taking so here logarithm is base 2, and this is 2 to the power of this cross entropy thing. And the perplexity, so what does it mean to be perplex? Like the meaning of the word. To be perplexed or something, yeah. Yeah. You're kind of like surprised in a way, or like you don't know what to do. So it's like confused. So perplexity is sort of like being confused, and this is basically what this metric is telling you, like how much the model is confused about the new sentences in the test data. If the model is less confused, so it's giving high probabilities to these test sentences, so then the model better understands the language. If the model has high perplexity, so it's completely confused about all these sentences in the test data, then it didn't really learn. So the lower the perplexity is, the better. Okay, does it make sense now intuitively? Okay, cool. Right, I mean, the lowest, what could be the lowest perplexity, by the way? What is the maximum, or sorry, the minimum perplexity a language model can achieve overall? If you just look at its formulas, what could be the minimum of that? Yeah. Couldn't it be 0? Are you sure? What do you think? 1? Why? Exactly. The whole thing could be at least 0, I guess, because logarithm of probability will be, well, minus logarithm of probability will be always, what is it? 0, bigger than like strictly positive. And you're summing them up. This is also strictly positive, summing them up. So everything will be positive here. And the minimum will be, if the probability is always 1, you get 0 here. So if everything is with probability 1, the model is never kind of confused. It says like 1 probability to every instance. Then this will become zeros, and 2 to the power of 0 is 1. Okay, so 1 is the lowest perplexity, but it's like in practice, it's actually impossible, to achieve. So the lower, the better. And of course, you cannot compare two models, train and test it on different tests. I mean, you cannot compare two models, test it on different test sets. So you have to always compare on the same test sets to make sure comparisons. So perplexity is not like absolute metric. It depends on the test data, but it's the same like in classification. Okay, good. Any questions so far? Perplexity and cross entropy? Sounds good. Okay, so shortcomings of n-gram language models now. I mean, we talked about them already. You figure out, so long-range dependencies is a big deal. Like capture dependency between the next word and the word's 10 positions in the past. We need to see 11 gram in the text, but we will never see like a sequence of 11 tokens twice in the data. Like very unlikely, very unlikely. And of course, it doesn't generalize across context, because if you know like black car bigram and blue car bigram, it doesn't tell you anything if you then see like red car. I mean, it doesn't have any sort of generalization of black, blue, and red, because these are distinct tokens. There is no sort of like understanding of the meaning of the word. That's kind of bad. So these are the kind of disadvantages. But the n-gram language models were actually super powerful up until, I would say, like 2010, 2012, 13 in many domains, like speech recognition, use n-gram language models. What else? I guess machine translation also used some n-gram language models as a backbone, like before 2015 when everybody jumped to the like deep learning models. So these has been very powerful, and it's actually very easy to train. And some of the biggest n-gram language models have more parameters than ChatGPT, like 700 billion parameters of n-gram language models from 2007 by Google. It's kind of interesting, like to see this kind of, But you need a huge table of these counts. You're basically counting the internet, and if you have like 7 grams of a huge vocabulary, make the math, and you end up with number of cells in your big matrix or big kind of tensor. So these are kind of big things. Okay. So can we use how would you, so now we know how to do the probability of next word given wk minus 1. So we know, for example, this trigram probability. So how do you now generate, can you generate text? So if you start, let's say, you start with S. So always there's a start of the symbol. So what could be the next word you're going to generate? How do you going to generate the next word? You want to use this for language generation. Can you do this for language generation? Of course you can, but how would you do this? Like, how would you get the next word to be kind of outputted? Like, how would you output the next word? Yes? Okay. So you're saying we have our probabilities already. So we can ask the model, what is the probability of word I, or what is the probability of word something something, given S? We can do this. And you can ask the model, and then you would say you pick the word with the highest probability. Sorry, I didn't get it. Actually. Oh, yeah, that's right. So if you take just the word with the highest probability, which would be maybe I, and then some other words, which means if you do it again, every sentence would start with I, which is kind of bad. So how would you go about it? I mean, do you understand what it means? Like you pick the highest probability all the time, so you get this basically always like deterministic output in a way. So what would you do about it? You can sample from the distribution. Yeah, exactly. Okay. So basically, this thing is a probability distribution. Like, I mean, everything sums up to 1 for all words. So for all words, it sums up to 1. So you have a probability distribution, and you can sample from a probability distribution. Can you sample from a probability distribution? I mean, there's libraries to do so. You can even figure out the math, whatever. You have a bunch of things. They have different probabilities, like a histogram. It's basically a histogram. So something is more likely, something is less likely, and so on. And you're going to say, okay, let me pick, according to this probability distribution, let me pick a token with which going to be this. So sometimes this is going to be I. Sometimes you're going to sample something different, which is going to be, let's say, V. And you can sample from this distribution. Okay, doesn't make sense? Cool. And this is it. Well, this is how language models work. They ask for the probability distribution. So we start, predict probability distribution over the vocabulary condition on the start symbol. So we start with the start symbol and then draw the first word from the predicted distribution. And then we say, okay, in the next round, predict the probability distribution over the vocabulary condition on the start symbol. And now we have also the first word. So we generated S, we generated I. Now we're asking, what is the next one? We draw the second word, which is going to be I like, whatever. And so on and so on. So we continue here, this in the loop, until we reach some special symbol, which is could be like this, end of sentence or end of sequence or EOS. So something, something, and once we get end of sequence, we stop the procedure. And basically this randomness here, draw the first, drawing from the probability distribution is giving you some unpredictability in the generated output. And this is actually the very same thing why ChatGPT or all these language models are non-deterministic, because they don't take like the next word by the highest probability. They always they sample from the token distribution. They sample the very likely next word, but not always the same. And that's why it's make it like every time very much different. And if you recall do you recall the temperature in softmax? Yeah, the temperature in softmax is, tuning this temperature is making this distribution either more uniform or more spiked. Like this is spiked. This is like there is one which is very spiked and everything is almost 0, and this is almost uniform. So of course the temperature controls the randomness of the distribution. So with higher temperatures you get more uniform distribution. Yes, with high temperatures, it's going here, so it's a high temperature. And the output of the language model will be more random. If you have small temperature, this will be almost deterministic, like not 100% deterministic, because these will never be zero because of the temperature and how the softmax works, but most likely it will be almost deterministic. This explains to you like how ChatGPT works in sampling language. You have the temperature, you can, I don't know if you can do it in ChatGPT, maybe in the API or some other language models, but you can set temperature, and it kind of governs like how random the output will be in sampling. But now you know exactly how the sampling of the words work. You just ask, what is the conditional probability distribution of the next word, and sample from this distribution. Okay? Any questions? So this is language models, but this is, I mean, we're talking about n-gram language models. So they, you know, these are not like ChatGPT, these counting, dividing, very, very short context. But before jumping to narrow language models, we should talk about a concept called word embeddings. So the task we can solve now, I mean, the motivation for using something called word embeddings, we will explain later what embeddings means. So I'll give you a task now. I give you a large corpus of some plain text data, and I want you to build a model that will answer some of these so-called like word analogy tasks. So for example, German to Berlin is like France to, what is the answer? So Germany to Berlin is like France to Paris, exactly, like the capital. So if I give you the state, the country, you should get the capital of that. Or man to king is like woman to, say it? Queen, yes, queen. So these analogies. So can you build a model that will give you some sort of these analogies, like comparing things and seeing analogies between concepts, and just do it only using plain text data and everything we just learned so far? That would be pretty cool, right? I mean, it would be really, because what is it telling? Like, not only we understand the meaning of the word, but this meaning of the word can be used to make these analogies of these words. So we know that hot and cold is the same as dark and light, like the opposite, something like that. Or I don't know, something like that. Some of these analogies, we can try to do this. So we're gonna do this. We're gonna build this thing, and it's gonna be actually at the end it's gonna be actually pretty easy. But this is like a nice consequence of building these things. Like we can solve tasks of understanding words and their meaning in context, not in context, in analogies. So for that we need to understand a few things. And let's start with the dot product. So what is a dot product? A dot product. I have two vectors. What is a dot product? I have two vectors. Oops, wait a second. Yes? Multiplying components and summing them up. Okay, so this is the formula you know. Does it have any meaning? You're not sure. Okay, you know how to compute things. This is good. But we should understand what it really means. That's why we're doing this. I mean, so let's start with dot product. And let's talk about the geometry of dot product, because it has some, it has a geometry. So let's start, with something very easy, like n-dimensional vector, so 2 dimensions, x1, x2. And we have these two vectors. I mean, these are dots basically, but I'm using these as an arrows, as vectors, okay? So this is like geometric representation. Everybody's with me? Sounds great. And now what you say, what is the dot vector, dot product, is this thing. You take each dimension, so now it's 2, and you multiply basically the coordinates for each of the dimensions, sum them up, and you get the dot product. So this is the algebraic kind of formula. It has also, I mean, look at this now as a let's say as a triangle. If you look at this as a triangle, you can start thinking about, the geometry of this dot product, what it really means. So it also has a meaning, which is the geometric. So you take, what is this thing, by the way? Yeah. Say again? The length. This is the length. So this is a L2 norm, which is the Euclidean Euclidean norm, aka the length of the vector. So basically, this is the length of the vector u. Okay, good. And if you look at the trigonometry of these things, you get that the dot product corresponds to the length of the first vector, the length of the second vector times the cosinus of theta. Oh, okay, that's really interesting, because now if the length were 1 for both, then the dot product corresponds to cosinus of the angle between these two vectors. And now you can understand, like, cosinus for what is cosinus? So when cosinus is 0, for which angle you get cosinus 0? Yeah, for 90 degrees. For 90 degrees, you get cosinus 0. And if the cosinus gets smaller, you get close to what? To like a no zero angle, basically. So the smaller the angle between these two vectors, the bigger is the cosinus of that, and it has 0 if these are how's it called? Oh, I forgot the term. Not complementary. Jesus. Oh, like right angle of these vectors. There's a word for that. I forgot. Say again? Orthogonal. Yes, thank you. Yeah, orthogonal. Exactly. So now you see, I mean, you have to multiply this by the length, but if these lengths were 1, then the dot product corresponds to the angle between two vectors. So there is some geometric interpretation of the dot product. And there's some scale projection. So, but let's have a look into, I mean, if you can do this like by simple geometry. Like, it's basically projecting one vector to another under the 90-degree angle. So this is really interesting. It has some geometric properties. But coming back to this, if we had these 2 unit vectors, then this is exactly what we just discussed. So this is length 1. So this is the unit circle. So they have length 1 times 1. So the dot product corresponds to the cosinus of this angle theta. And exactly as we just discussed, angle theta for 0 is 1. Then it goes by 90 degrees. It goes to 0 and then oscillates like that. So if you rotate these vectors, you get a different cosine, you have different dot products. So the dot product has a meaning, like somehow, like, do these vectors go in similar direction, or do they go orthogonally, or do they go like in opposite directions? And you get the different results of the dot product for unit vectors. Okay? Any questions? Now, does it make a better intuition now? A little bit, hopefully. So it's not just the algebraic, like you multiply and sum up together. It has a meaning, and it's really important to understand this meaning for later on why this will be any useful. Now, and of course, if these are orthogonal, so like W and U, we get 0. Okay, so they are kind of pointing to completely opposite, to like independent directions. All right, and the least similar is if it goes, the other way around. So if it goes completely 180 degrees, you get a -1 cosinus. Okay. So now, I mean, these were, on the circle, but now, of course, this is, we have the dot product is unbounded. It's always, if, for UV, I mean, this is smaller than 90 degrees, so this will always be bigger than 0. But how it happens, like, if you make this vector longer, like this would be, let's say, a vector W. So what happens with the dot product? Will it be smaller or bigger now? Exactly. So yeah, the norm will be bigger, and we're multiplying by the norm of these two vectors, so it will be bigger. So I would say U times W will be bigger than this one, because we're growing, and it's exactly what happens. So, oh, and now you can see, yeah, that's right. I mean, the bigger we are making one of these vectors, the bigger the dot product is getting, and it's unbounded. So it could be basically infinity. I mean, it goes infinitely, arbitrarily large, if you will. So there's no bounds. Now, what happens if we have the vector of the opposing direction? So it will be now these two. So it's going to be, let's call it y. So these two vectors, the dot product of these two vectors will be what? It will be -1, exactly, it will be negative, so it will be smaller than this, and that's actually true. And then, of course, now you can see, like, oh yeah, if we make this bigger, then the dot product is becoming what? Even smaller number, like a even smaller number of uz. So now you see, okay, so this is interesting. So it's not, the dot product not only depends on the angle between these two vectors, but also on their length, because we're kind of multiplying by the by the Euclidean norm. And now you can think like, oh, you know what? I mean, does it have something to do with the distance of these points? So like these 2 points are close to each other than these 2 points, or these 2 points, or these 2 points. So like Euclidean distance between points is a thing, and now we have this dot product. It's also like if the vectors are far from each other, there should be also closer, far from each other as a Euclidean distance. Okay, so there is a correspondence which I'm gonna skip right now. But if you do the math, you ended up with like Euclidean distance is this is the L2 norm for 2 vectors. You subtract each dimension, make it squared, and take a square root of the sum. But the thing is, at the end of the day, the dot product is actually the negative of these of the dot product. So, excuse me. The Euclidean distance is -2 times the dot product of these two for unit vectors, and there's some other thing. So basically, if we want to minimize the distance between 2 vectors, we can as well maximize their cosine similarity. Okay. So if we want to make 2 points in a space very close to each other, which means the Euclidean distance is becoming very small. The Euclidean distance is just the line between these 2 points. So we want to make this as small as possible, maybe. It corresponds to making their cosine similarity as big as possible. And there's exactly like, this is the correspondence of that, which you don't have to remember or whatever. I mean, there's some correspondence. But just this meaning of the dot product is like the dot product becomes bigger if we're minimizing the square distance and if these 2 vectors are normalized. Okay? So this is somehow what we need to know about the dot product as an intuition for using this later on for, if you see like minimization, you can already guess, what we are going to use it for. What we're minimizing all the time. We're minimizing some losses. So we might use it in the loss, or we might use it for some, like pushing things together by distance or pushing them far away. So this is exactly what we're going to use the dot product later on. Okay, so this was a tangent, but I think it was an important one, because if you just see the formula, the algebraic one for dot product, it's kind of like, why? Now there's a geometric intuition of the dot product, why this is actually helpful for doing things that we're doing. Any questions? Very cool. Okay, come back to language models. So the task of language model is to, it's a conditional probability predictor. So given a sequence of keywords, return a probability distribution over the vocabulary for the next possible word. So this is what we were discussing like 20 minutes ago. So in detail, give me a probability of something given the previous for all possible words for vocabulary view. So this is it. This is the summary of the language models. Actually, it somehow looks like just a classification task. It's basically saying like, isn't it? Like let's do a refresher on what is text classification, right? We had text classification already, like classifying a sentiment in movie review into positive or negative. We have this already, text classification. So what is text classification? So for text classification, given a text, and we talk how to turn text into bunch of numbers, one-hot encoding and stuff like that. So given a text, predict its label from a set of arbitrarily ordered items. So we have classification, for example, as sports, politics, and travel. And we model the conditional probability for each label, which is a probability distribution over all the classes, for example, by softmax. We have this. Like we take the the one-hot encoding, push it through some network, and at the end of this network, there is a softmax, which is giving the probability distribution over the classes like sport, politics, and travel. Does it ring a bell? It should ring a bell. If it doesn't ring a bell, it's time to start learning. Okay. So, and why I put these kind of bold words here will be very clear in the second part of this slide. What is a language model? Given a text, predict the next word from a set of arbitrarily ordered items, which we call the vocabulary. We model conditional probability for each word, a probability distribution over the entire vocabulary, for example, by softmax. I think it's basically the same task. It's basically a classification task. We're taking input, which is we take given a text, so these are the previous words. We predict the next word. We basically classify the output into a next word. I mean, now we're not classifying over 3 categories, such as these 3, but how many? We're classifying over the size of the vocabulary. So there will be like 50,000 classes, which we need to classify into. So which we do which we kind of push, for example, by softmax through softmax. So here we are doing softmax over 3 classes. If you remember, softmax was like this: e to x I over the sum e to this is sum. This is sum e to the x j. Sorry for my handwriting. This is some sort of softmax. Okay, you should remember softmax already. And we're doing the same over words. I mean, we're basically under the hoods, we're classifying a piece of text into one of the categories, which corresponds to the vocabulary, which corresponds to the next word. But we're using the same underlying, conditional probability kind of model. Okay? Do you see the analogy or not really? A little bit. There is some analogy. It's a different task in a way. Like it has a different meaning. Like we're predicting the next word, but actually what we're doing, we're taking a text and try to classify it into one of the 50,000 classes, give a probability distribution over those, and then sample from this distribution the next word. This is it. So this is cool because we know how to solve this. We know how to do classification of text. So which means we can build a neural network to do this classification and do the prediction for the next word. We can do this. So welcome to neural language models, which is not based on counting and dividing, but it's based on something else which we will have to find out. So, but let's start with building a neural network to solve this task. So for now, you should already know everything which we talked until the last lecture and the exercises. What is a neural network? What are these inputs and things like that. I didn't use the lingo of the standard neural network, so we didn't talk about neurons. We talk about activations. That's right. We didn't talk about neurons, but we talk about layers, and we took this perspective of functions. So there is a function, linear projection, and nonlinear activation. So squeezing this through all these kind of sigmoids, rels, and stuff like that. So you should be very familiar with that already, because these are the building blocks we're gonna use everywhere. So everybody's fine with that. Like everybody knows how to build a neural network. We're gonna use the convolutional graph kind of thing again, which is a network. It's the same thing. Okay. So what should be the input now for this network? So let's say we're gonna build a network which is gonna look like, I don't know, there has to be some vector here. It goes to something which is gonna be deep because it's a neural network, and here's gonna be something else. That's a neural network. So the first question we need to solve, like what is going to be input here? So again, given a text. Okay, so if we're saying given a text, there should be a text. So what should we plug in here? Any ideas? Our goal is to predict, given the previous words like the lazy. How was your sentence again? The lazy dog barked, and we want to find out loudly given this. Okay, so this is our input. So how do you turn this into input of a network? Yeah, I put a lazy dog here. Somehow I put the lazy dog barked here. I need to put it here. But how? How do I turn text into something like a vector? Yeah. One-hot encoding, exactly. Yes. One-hot encoding. Yes. This is not new. I mean, you know everything, or you should know everything now. So one-hot encoding goes here. Okay, good. Then something happens, some magic here, whatever. Could be, I don't know, relu, linear projection, relu, blah, blah, blah. And here comes something which is what? So what's coming out of here? It's going to be vector. It's going to be vector in some dimensions. How many dimensions is going to be out here? Yeah. As big as our vocabulary, because we want to get a probability distribution over this vocabulary. So this is going to be vector of the size of the vocabulary. And it's going to be a probability distribution. So it has to sum up to 1. Because we're going to sample from this or predict the probability. What is the probability of loudly after seeing your favorite sentence? And this will be here. So this will be like 50,000 or how many items? Yes. So you are asking, how the hell are we going to one-hot encode this sentence? And we have many options, and we'll talk them through, because some will be much better than others. The very naive one, I'll tell you like very naive one. You take the first word, they get a one-hot encoding, which will be 50,000 length zeros, and one will be 1. First word, then you take the second word afterwards, and you concatenate all these words into like very large vector, and this could be your representation of the input. Is it the best one? Maybe not. Maybe there's better ones. We'll figure out. But this would be like the naive kind of baseline thing. Any questions? You know this already. I mean, you should know this already. This is a simple neural network. Take the input, produce the output. But we just use it for language modeling now. Like you have, the shift of predicting an expert is actually like doing classification over the input, like to classify it into words in a way. Why not? It's the same kind of formula in a way. Okay, good. So this is exactly what we did. So the input would be some sort of k-gram of words, 1 to k. Of course, we don't want to. I mean, maybe you want to have it unlimited, but let's take some n-gram first, like k-gram, few words, and the output is the conditional probability distribution over the vocabulary for the next word. Okay, so we had it already, and we talk about like how to turn this input text to the vector, and I'm gonna show one example, which is not as baseline. It's already somehow more important. But okay, let's look at this. Let's look at this thing again. Let's take it from the back. So what is this? What could this be? We're gonna train this bloody thing. So what is the output of this computational graph all the time? We need to minimize something. Yes, it's a loss. Of course, loss. Which loss can we use? Yeah. Categorical cross entropy, because we're classifying after softmax into, we're comparing output of softmax with another distribution, which is one-hot, so we need categorical cross entropy. Exactly. So this is going to be categorical cross entropy loss. Good. What is this? Yeah. This is gold label. Okay. Interesting. So this is the gold label. So what is going to be gold label for a word? What could a gold label for a word be? Say again? The word itself, but you need to turn it into a vector, which is one-hot encoding. Exactly. So it's going to be one hot of the word, of the target word. Say again? Of what? Loudly. Loudly, yes. Of the target word, which is loudly. Yes, the word loudly. Okay, so we have this. Now, okay, so this is softmax of, this is linear projection. These are parameters. So there's just some mapping from some space to another and going through softmax. So everybody should know softmax. We don't have to discuss. Then there is another, let's say, the first sort of projection to some other space. And what could the G here be? Some nonlinear function, for example. For example, ReLU. Yes, I'm fine with ReLU. ReLU sounds great. ReLU. And these are some trainable parameters. Okay, so we understand now like pretty much everything so far. Now The question is like how we turn these 3 words into a bunch of into a vector. And as I said before, we can concatenate the one-hot encodings, but maybe that's not the best thing. We're gonna use something else. We're gonna turn, so this is basically D, black, and dog is gonna be one-hot encoding. So 0, 0, 0, 1, 0, 0, 0, of very large size, like size of the V. We need to turn it into something which is smaller. So we want to turn it into smaller vector. How do we turn it into smaller vector? Like something which is not like 50,000, but maybe 500. Yes? Oh, this is interesting. So you're gonna associate the word the with some class. How do you do this? That's a tricky question. We don't know the answer, but it's a good intuition you're having. We're gonna turn the word into something different. We're gonna turn it into some smaller vector, and we're gonna look this up. I mean, we're gonna use some matrix which contains our entire vocabulary, and for each word in the vocabulary, there will be some small vector. So for example, 50. So here's, let's say, smaller vector, say 50. So this matrix E is a matrix of size of the vocabulary times what I'm interested in, the 50. I don't know what is in there. I mean, there could be something which, as you might see, which we can actually learn because it's a parameter. We can learn this by backpropagation, like by training, we can learn these things somehow. And so again, the E, we call it the embedding layer. And what we're gonna do is that, I mean, the input are symbolic categorical features, so one hot. So for example, the word the dog is 0, 0, 0, 1, 0, 0, and so on. And we want to turn this into some, let's say, 50-dimensional vector, which would say the dog is something smaller, and there could be some numbers like 0.25, minus 3, 365, and so on. Some numbers, but dimensionality of that will be much smaller. So this is like, this is the size of the vocabulary, and this is 50 only. So the question is like, why? Why is it any useful where I get these numbers and what they mean? But it's basically like trying to represent the word somehow differently. Like you're not representing as a one-hot encoding, but you represent it as some other vector. And you want this represent as vectors which give you some good advantage. I mean, they are more compact, yes. It's a passport of the word. Okay, interesting, yes. Like an identifier, like each word has a passport, and you can look up in the passport for some important things about the word. That makes sense. Why not? Yes. Yeah, okay. I mean, you can describe a word as I'm one of these 50,000s, or you can say, oh, maybe, this word is it's an adjective, and it's past tense, it's something, it has a color, and things like that. So yeah, I see where you're heading to. So and this is the idea. Like we want this representation of the word to have to carry some meaning of these words.
Can you also maybe think about it as a point in some sort of space?
It is a point in a space, yes.
And then similar words are in the same.
But you know it already, right? Kind of. Yes. You can think about this like each word. Now we're turning each word from like higher dimensional space, and these are all like different. We're turning them into some smaller space of 50 dimensions. It's still kind of. Let's think about these as 3. Let's think about 3 dimensions. So let's say we kind of take all words from our vocabulary and put them into this room. And what you're saying is that, well, you're saying like similar words should be close to each other somehow. Is it what you're saying? And that's exactly the point. Like We want to give them such properties that similar words in meaning, and now you can argue like what's meaning of the word, blah, blah, blah. But we want them to be somewhere close to each other. So for example, like a dog and a puppy, or I don't know, like a cat or kitty should be somehow close to each other, like in this, in this corner, and some words like, I don't know, some other words like countries like Germany, France, and so on should be somewhere in other place of this space, sort of. What exactly, how we are actually constructing the space, it's a question, and we don't know, and we actually don't care. We let some algorithm, we want to train the model and to decide what is the best representation of the word. We want to learn this representation of these words. That's the advantage. We're not going to create a passport saying like this is it, it's a noun, it has these properties, it's about color or whatever. We're going to say there will be some kind of check marks in the passport of this word. There will be some numbers corresponding to these check marks, but we don't really tell a priori what these are. And dear model, let's figure out. Okay? So do you get intuition now? Like, why are we doing this embedding? Turning the representation into something which is much more easier to work with. And these vectors are the parameters of the model. So they will be trained with other parameters. Now, I use this kind of thing called lookup. So what does it mean, the lookup? So I need to turn this one-hot representation into some vector corresponding to the row of this embedding matrix. So it's actually very easy. So let's say word number 48 is, let's give me an example. So one-hot encoding, let's say the dog. The dog is 0, 0, 0. At position 48, this is 1. So this is position 48. And all zeros. And in the embedding matrix, I have all these. So this is the size of the vocabulary. And this is, let's say, 50. So at position 48, this vector is the representation of the dog. I'm basically looking up. How can I do this very efficiently? Is to take this and multiply by the matrix. Like take the one-hot encoding vector, and what happens if you multiply this by this matrix is basically you end up with getting just the numbers in this row. It's very efficient. Like, you get it? You take, okay, so multiply this with the first row, with the first column. So 0, 0, 0, 0, 0, 0 plus 1 times this entry plus 0, 0, 0, and so on. And why is multiplication great? Because you can parallelize it, you have all the GPUs, and it's very efficient. So multiplying matrices is awesome. So if you can turn everything into multiplying matrices, you're saving time. And this is how we get the embedding from the embedding vector. So there are some numbers. We don't know what is there, some numbers, but we can pick up representation for each word. Does it make sense now, the lookup operation, what we're doing here? Any questions? So now everything now here should be somehow clear, I guess, because we take the word in one-hot encoding, we turn this into the lookup vector from this embedding matrix. Oh, we didn't talk about this. We concatenate these three after each other. So after that, we get a vector of, let's say, 150. Right? We take the first word, second word, and the last word, turn it into embeddings, and just concatenate after each other. So we get like 3 times 50 is 150. So now we have a vector of size 150, and we plug it into the neural network. That's it. That's fairly easy. Does it make sense? Any questions? Anything which you don't understand on this? Yes? Oh yeah, if we are at the beginning of the sentence and we don't have even like 3 previous words, so what would you do? Like the easiest solution to this? Like zeros. Well, let's start with the words. Like, which words would you put in? We had the S start of the sentence. So, yeah, we might say like S1, S2, S3, and then start like 3, or just saying 3 times there's S, like at the beginning of the sentence. Exactly. Very engineering-wise, hacky solution. It works. Any other question? Sounds great. Okay, so we won't finish this full thing today, but it's okay. I mean, we can continue next time. So we talk about the embeddings and lookup operation. Okay, so let's simplify the notation. Okay, so let's I turn the embeddings into V, so it's gonna be V vector. Then we have a concatenation. I turn this whole thing into something which I call linear layer. So there's linear layer with these two parameters. So this is now trainable. There's this nonlinearity, which is going to be the ReLU. There's another linear layer with another parameters. Then there's the softmax and the loss. And here, yeah, this is the target word. So the black dog is the input. I'm going to concatenate these three words after each other. So first, second, and third. And I'm trying to get to train the network so it can predict bark. So this is the signal I'm giving it. All good? Excellent. And we now to train this bloody thing. We want to train this as a classifier. How do we train a classifier? So we need the labels and we need the training data, like X and Y's. We need this data set. Very, very many examples. And it's actually the same as we did for training the standard count-based language models. We take a corpus, just take the internet, chunk this into k-grams, and the first k-1 words are use these features, so inputs. And the last word is use the target label for the classification. Like you start with your Wikipedia and say, okay, so the black dog barks, then take the next kind of chunk it, and these will be your training examples. So there will be many of them. Okay? And as we said before, this is our training data, and we're gonna use the loss is gonna be the categorical cross entropy loss. Yes. Exactly. The embedding layers, its weights we are training. So this is trainable parameter, and we're training this. Can we train this? Can we backpropagate through this? So can we actually backpropagate through this network? Because this is a computational graph. We train it by gradient descent and backpropagation. Gradient descent and computing gradient by backpropagation. So can we do backpropagation in this thing? So let's think about it. I mean, until now, like this, everything is a standard MLP. What is MLP? Oh, okay, start learning. Multilayer perceptron, the basic building block of neural networks, MLP. Can we backpropagate in this feed-forward network? We can. We did this already. It's a neural graph. Okay, and now the question is like, can we backpropagate through this concatenation and lookup? Sure, we can. Concatenation is like you have 150 inputs. What is the partial derivative of this? What is partial derivative of this output with respect to each of these inputs? 1. You get a gradient of this concatenation. You know why? Yeah, it's 1 because you're taking number in, so it's basically a identity function, and the identity function. So is it? Yes, I guess so. Is it 1? Yeah, it should be 1. So you can backpropagate through this node. You can backpropagate through the lookup as well, because the lookup is what? Oops, excuse me. The lookup was a multiplication of vector by matrix. It's a multiplication, so we had this simple product node which you can backpropagate through, so you can compute the derivatives of this as well. So everything here, all these functions are differentiable. Here, all these functions are differentiable, so you can backpropagate back to everything here, to this E embedding matrix, which is some parameters. These are parameters you train, so you can backpropagate to everything and take a step and do the training in gradient descent. Does it make sense? Like everything here is differentiable. So it has to be differentiable functions, and the only thing you need to know, like, to implement the output of the function of each node and the partial derivatives with respect to the arguments of this computational graph. There's everything, as long as it's differentiable, you can plug it into a neural network and just train it by backprop, SGD and backprop. Yes. Okay. How do we? Oh, here's another question. Okay, so how do we start? Now we have this data set. We have the architecture of our network. We start training with stochastic gradient descent, but we need to start with some. How do we initialize these parameters? Like, how do we start? What should be the starting parameters? Where do we start? Any ideas? The simplest solution ever. Random. Exactly. We randomly initialize all the parameters, which means we randomly initialize the embedding vectors. So the embedding vectors were going to be very bad at the beginning of the training. But once we start training this language model, saying like, okay, after seeing this, what is this word? What is this word? I mean, at the beginning, the loss will be horribly high because the network will just make all these kind of it doesn't understand language first. The embeddings are just random vectors. Like the and black and dog will be as random as any other word at the beginning in this embedding matrix. And you start, you compute the output, and it's gonna predict the black dog. It's gonna predict a sun, which is completely not the word bark or barks. So you backpropagate, update the parameters, including the embeddings. Okay, you take the next example, like give me your second favorite sentence. Do you have a second favorite sentence? No, this is like your first favorite sentence. What is the second favorite sentence? Okay, let me go on. I want to go home. So I want go home, and of course, it will predict something completely rubbish. So I update the parameters again. I'm doing this over and over. I will start learning some good parameters of E, and the loss overall will go down. So which means I learned how to predict the next word after seeing this by learning these parameters, the projections, and the embedding parameters as well. So I will learn, after this training, some very good representation of words. This is cool. I'm gonna learn how to create this passport for the words. I'm gonna learn how should I describe the word black so that in this configuration, it can predict the next word after. And that's gonna be pretty cool. So there will be some properties of these embeddings which will, as you said, like some words should be closer to each other in the meaning. So yeah, exactly. Because if you have the black dog barks and the gray dog barks, then black and gray should kind of give me almost the same prediction. So their embeddings should be closer to each other because they should give me the same output or similar output. So that's why we're kind of trying to. That's why this network learns the embeddings in a way it learns the embeddings. Yes. Yeah. Yeah, exactly. Exactly. That's the point. So now we have the embeddings matrix which we trained, and then we see here the vector for 48, which is dog, and the vector for 127, which is I don't know, a cat. We can compare these two vectors and see like, are they similar or not somehow? Can we do this? Sure. Like we can look, oh, by the way, so we have two vectors. Let's take, this is not 50. Let's say this is just 3 dimensions. So we can look into like how far they are from each other in the 3D space. But we talked about something else today. Not the Euclidean distance, we talked about something else of vectors. The dot product and the angle between vectors. So if they're close to each other, their dot product should be smaller angle, higher dot product, close to 1. Depending on the normalization, if you normalize them, it should be close to 1. But should be higher, like the cosine distance, or sorry, the cosine similarity or cosine distance or dot product should be higher for words that are somehow close to each other in this space than for words that are completely different in this space. This is the intuition of the cosine similarity. I mean, Euclidean distance will give you somewhere as well, but the cosine similarity is actually very nice. And it will be used later on for training some little bit better model than this one. much faster. So let me just wrap up here. So this is how we train the neural network model. And by, yes, so now we just use, so just to wrap up, like I'll say like maybe 2-3 slides and then we'll finish for today. But we just used here, I mean, you might be asking now like, oh yeah, we had like count-based models, counting, dividing, and we had 3 previous words and the next word, but now we have the same thing, but it's much more complicated because we're not counting and dividing. We're doing like some crazy stuff in neural networks. Like, why should we do this in the first place? I mean, you might be saying, oh yeah, we're learning these embeddings. Okay, so this could be a nice byproduct. But for the language modeling task, it's not, maybe it's helping us, maybe not, but we still have the limited context. We didn't solve the problem. I mean, we solve here with the problem of generalization because the black dog and the gray dog will have some similar, will produce a similar output probabilities for barked because there is some transfer of these similar words because of these embeddings. So this is the first problem of the classical count-based models where 2 different words were completely different, like gray and black, completely different words, no semantic meaning whatsoever. So we're solving this problem now. But we don't solve the problem of like, oh, the long context. We should need like not just 3 previous words, but more. So what can we do? Can we add more words? How would you add more words like context here? Yeah. No, I would just add it here. The lookup is the same. I just added here. Yeah, okay. No, not the word to the vocabulary. The vocabulary is fixed, but to the context. Yeah, okay, let me adjust new words. So we're increasing bunch of parameters. Yeah, we're increasing bunch of parameters here because if we're concatenating, I mean, now it's turning from 150 to 200. So the length now is going to be 200 because we have 4 times 50. And this has to be larger. I mean, there will be some increase in parameters in this layer because we're getting more. But let's add another word. So another V and add in here. So we're getting 250 now. So this is increasing. But now you see the increase in the number of parameters is sort of linear with respect to the context. And if you think about the increase of parameters in the Ngram language model, it was exponential in a way. Like was the vocabulary, again, you would be multiplied, if you add 1 word to the context, you would multiply the number of parameters by the size of the vocabulary, like 50,000. Now we're just adding 50 rows to this matrix, or 50 columns to this matrix. Rows, yes. So this is cool because we can increase the parameters with K1, so it's better than classical. So a linear increase in parameters. And as we say, also kind of get the intuition, we learned word representations as the sort of like byproduct. We are doing language modeling here, but it learns some cool representation of words, where the similar words are somehow to be closer to each other in this, in this embedding space, and they should have higher cosine similarity or smaller Euclidean distance, however you want to call this. Okay, any questions? Good. This is for today. So next time we'll finish some more efficient algorithm than this for word embeddings and how this could be used for doing cool stuff. Solving the task like France to Paris is like Germany to. We don't solve it yet, but now if you think about the embedding matrix, you can think about this. Actually, we have in the embedding matrix, we should have everything for solving this task already. Okay, thanks a lot and see you in the afternoon.